Hi folks. In this video I want to talk through how to think about the last problem from the Hooke's Law lab homework that you had, where you were asked to use pie charts to represent the energy transfers in a system that includes a spring, a box connected to that spring sitting on a surface, and all interacting with the earth. So this box is pulled back to some position called X max, and then it's released and it's allowed to oscillate back and forth until eventually it comes to rest. But before describing how to think about this system, I want to refer back to the Hooke's Law lab that we did. In this lab, we measured how much a spring was stretched when varying amounts of mass were hung from it. And we graphed what we called the spring force, that was the spring reacting to the mass hanging from it, versus the displacement, and we found that it was a linear relationship. So the name of that relationship is Hooke's Law, and the relationship between the spring force and the displacement that Hooke's Law describes is written this way. The proportionality constant between the displacement and the force we call K. K is the spring constant, which refers to how stiff a spring is. And because the displacement and the force of the spring are acting in opposite directions, in other words, the spring is acting to resist the displacement, we said that that was a opposite relationship. So we put a negative sign in front of the kx. And then we also agreed that if you think about it in terms of how much energy is stored in the spring as it's stretched, and if you represented that by a pie chart, then there seemed to be some correlation between the energy under the force versus displacement graph and the amount of energy stored in the system. As the force increases, so does the stored elastic potential energy, and so does the area under this graph. And based on that qualitative relationship and that qualitative reasoning, we derived an expression for the elastic energy that's stored in the spring as equal to the area under that curve, which is 1/2 the base, which is measured in displacement, times the height, which is measured as the spring force. And then if we substitute for the spring force the equation for Hooke's Law, then we get this expression 1/2 times kx times displacement is equal to the elastic potential energy, which simplifies to 1/2 kx squared. So let's consider for a minute a system of a spring with a hanging mass on it. Let's put 100-gram mass on this spring, which brings it down to a new hanging equilibrium position. We call that the equilibrium position because it's at rest. The force pulling down on it is equally balanced by the force pulling up on the spring. So if we don't do any work on this system, meaning if we don't transfer any energy to it, it will stay in equilibrium. But if we displace it by some amount, for example, by pulling this mass down and then letting it do its thing, bouncing up and down, the energy is being transferred to different forms of energy as it bounces up and down. If we're only interested in what happens to the energy we add to the system, then we can track its transformation from elastic to kinetic and back. And if some of that energy is lost to friction along the way, for example, if there's some damping, what we call damping in the system, then some of that energy is lost to friction along the way, and the system will eventually come to rest. So to return to the homework problem, you were looking at a similar system, but this time the spring is on a horizontal surface. And you were asked to consider what would happen if some force were applied to displace this mass to the right by some amount. up to a maximum displacement. And then if the block were let go to oscillate back and forth, it would do the same thing as the hanging spring. It would oscillate back and forth past this equilibrium position until it eventually came to rest. So if you were going to show what its energy looked like in terms of a pie chart at the beginning, then we can say that all of its energy is elastic potential energy. And then we can describe what happens to that elastic potential energy once we let the block go and start oscillating back and forth. So as the block starts to slide to the left, it speeds up, going faster and faster. And there's a point where it passes back through that equilibrium position, which would be the position where the whole system was at rest. Relative to the time before we stretched it and added energy to the system, we can call that the zero elastic potential energy position. And so when it passes through that point, it has no elastic energy. It has only kinetic energy and some amount of thermal energy that's been lost as it slides across this, the surface. The next position that we might consider is when it reaches full compression at the other end and comes to a stop. So at that point, all of that energy has been put back into compressing the spring. It's now all elastic potential energy, and it's gained some more thermal energy. And then it's going to start to oscillate back through that zero equilibrium position, at which point its energy is all converted back into kinetic energy, but it's lost more thermal energy, and so on. It will keep oscillating back and forth in this way, gaining and losing kinetic and elastic potential energy, and the whole system is losing energy to thermal energy. So at some point between when it's stopped and about to turn around and when it's passing through its equilibrium position, it has both some kinetic and elastic energy, and it will keep oscillating back and forth until all of the energy is converted to thermal and it will come to rest.